My name is Anders Hejlsberg. I'm the Chief Architect of C#, and I'm here to talk about what we're doing for C# 2.0, or the Whidbey release of C#, all of the language enhancements that we've been working on. They basically fall into these sort of 5 categories that I have on the slide here. And before I start talking about what they all are, let me first make sure that you all know that all of the features I'm showing here are actually in the alphabets that we've been handing out. So all of the demos I show here, and if there's something, I'll point it out. But that should all work with the alphabets. Another thing I think is tremendously important with all of these language extensions is that we've designed them all so that there are no new keywords in the language and no breaking changes. So all existing C# code should compile with all of these language extensions enabled. So it's just sort of a very natural evolution. Now, the big new thing, and I'm sure you've already heard about it, is this thing we call generics. But over and above that, we also now in C# 2.0 support anonymous methods and iterators, partial types, and a whole slew of other enhancements that I'll go through. But let's start first with generics, and I think the best way to actually understand generics is by looking at an example. I'm sure you have all, at one point in time, either written code like the code that's on this slide, or used something of the same nature. This is basically a little list class that implements a growable list of any kind of object. So it has an add method and an index or an account property and so forth. And really, it's basically a thing like the array list class that we have in our base class collection libraries. Now, use of this class would look something like this. I might new myself an instance of my list class, and let's say I want it to be a list of ints. Since I've written it to use object, I can put any type into this list. But unfortunately, if I just want it to be a list of ints, there are some penalties that I'm saddled with by using this general purpose type. First of all, every time I put ints into my list, they end up being boxed because ints are value types, and that adds overhead. Second, there's actually no compile time type checking here. I could add strings to this list as well, even though it wasn't my intent, but I would not know of the error until at runtime. And thirdly, when I take things out of my list, I have to cast them back to the type that they originally had. You see this typecast back to int down there. Now, with generics, and you sort of see sort of the thing that's missing here, the thing you'd really like to be able to do is to say that this is a list of something and be able to specify what it is a list of. And that is precisely what generics allows us to do. So with generics, maybe I should just go back so you can see that transition again here. On the list type, I am now permitted to parameterize my type. I can say it's not just a list. It's a list of some type T that I will give later, but I can now write the list in terms of that type T. So you'll see that I can, for example, have a T array of elements in the list. I can have an add method that takes a T. I can have an indexer that returns T's and so forth. And in use of my list, when I actually use it, I get to then specify that I am now creating a list of some type. In this case, a list of int. And now, first of all, I get no boxing performance. I'll explain why that is. Second, I get compile time type checking. I can only add ints to this list, and trying to add a string is an error. And thirdly, when I take things out of the list, no cast is required. Now, you may wonder, well, how does that actually work? First, when this list class is compiled, it's really just like a normal list without a type parameter. The compiler compiles it and produces IL and metadata. And of course, it encodes in the IL that there were type parameters on the class. And then later, when the list is used, so when the orange code box execute, the first time in an app domain that someone asks for an instance of, say, list of int, the system first looks to see, have I already created one of those before? And if not, then it takes the IL and metadata for a list of T, and it takes int32, feeds them to the jitter, and out the other end comes x86 code where T has been substituted with int. And literally, we end up with native code where all t's become ints. So in this particular instance here with list of t, I will end up internally with an int array of elements and an add method that takes an int, an indexer that returns an int, and so forth. Now, I've already alluded to some of the reasons why we're doing generics. You know, it's more stronger type checking at compile time, which is always a good thing. You find your errors sooner. There are performance benefits, you know, because we can avoid boxing, overhead, and downcasts. And also, we can really sort of make good inroads on the problem of code bloat of type collections. I'm sure you have all, at one point in time, had to sort of follow the manual expansion pattern of writing a customer collection and an orders collection and a products collection, et cetera, et cetera, et cetera. And instead of having to do that over and over and all of the bloat that encompasses, you can just write a collection class once and then simply supply type arguments. Indeed, if you think about it, with this class that I just showed here, list of t, you really sort of get to have your cake and eat it too. There has been, up until now, sort of this tension between, well, gosh, I like strong typing. Maybe I should use an array, a customer array, because then I can only put customers in there. But boy, a customer array can't grow itself and it can't sort itself and it doesn't have all the convenience methods. Or I could use an array list, but now I lose the strong typing. And so there was always tension between those two. Well, with generics, you get to have your cake and eat it too. You can have a list that, you know, is dynamically growable and sortable and whatever, but is also strongly typed. So I talked a little bit about already how C# generics are implemented. It's interesting to compare C# generics, for example, to C++ templates. I think the way I think of C++ templates is basically that they're sort of like super macros. It's really templates to sort of at the base work through textual expansion. The compiler performs textual expansion of sort of this gigantic macro. C# generics are very different. Generics get compiled to IL, and then the actual code expansion happens at runtime, not at compile time. And that makes it a lot easier for us to have code sharing strategies, and certainly does away with the problem of code bloat and eliminating redundant instantiations. Another difference between templates and generics is when does the type checking occur. In C++, when I write a template class, and let's say it has a type parameter t, and I have two parameters or variables, x and y of type t, I'm free to write x plus y. And, you know, as the template is compiled, that's fine. Not until I actually try to instantiate the template is it checked whether t has an operator plus. And if it doesn't, then things sort of fall over and you get some pretty cryptic error messages. With C# generics, we actually do all of the runtime type checking up front. In the sense that when I write a list of t, for example, unless I constrain t, and I'll talk about what that means, but unless I say something additional about t, the only things I can do on values of type t are the things that we know will always exist, i.e. equals and toString and all of the methods on object. And unless I add constraints on t, I just won't be able to do things that aren't there, so we can do much stronger type checking that way. C# generics work, as you saw on my little first slide, they're both for reference and value types, and indeed when they are used for value types, they give you the efficiency that you would have had if you had written it manually with that value type. In fact, the code sharing strategy of the JIT is that when you create type instantiation with value types, we create a new copy of the code for each value type. So with list, for example, if I have a list of int and a list of long and a list of double, I end up actually with 3 copies of the code, you know, only if I ask for those types, of course, and they get created dynamically at runtime by the jitter. But for all reference types, let's say I have customer, order, employee, product, classes, they actually all end up sharing the same native code because representationally at the lowest level, references are just pointers and we can actually share the code. So the jitter can be pretty, and the system can be pretty smart about how generics get implemented. I think it's just briefly interesting to contrast C# generics with the proposed generics in Java. Generics in C# are not just a C# thing. In fact, actually, VB will support them, VB.NET will support them, and they go deep into CLR, and there's knowledge about generics in the CLR. the proposed generics for Java actually work completely differently, and they're really just a compiler trick. The compiler, when the compiler compiles a generic class, it just takes all the T's and throws them away and puts in object instead, and then inserts typecasts and auto boxing and whatever. And so you sort of get the syntactic sugar, but you get none of the runtime efficiency. And the other thing that you lose is true runtime type information. So in C# and .NET, generics go deep, as I said, into the CLR. They go deep into reflection. Indeed, I can walk up to reflection and obtain the system.type object for list of T, and then I can arrive with the system.type object for int, and I can say, please bind yourself to int and give me a list of int, and I get the system.type for that guy, and then I can call activator create instance and dynamically create a list of int, etc., etc. So anything that I can do in my code, I can also do through reflection, and that's tremendously important in sort of this world that we live in today, where a lot of code gets dynamically generated. Whoops, wrong way. Now, type parameters can be applied to many different types, not just classes. Indeed, they're permitted also on structs, interfaces, and delegate types. And on the slide here, you see sort of some examples of it. And you can have many type parameters on a class. For example, a dictionary might have two type parameters, one for the type of the keys and one for the type of the values. And here you sort of see some other examples of generic types. Speaking of the dictionary, when it's being used then in the constructed types, we can look at some examples here. For example, I might have a dictionary of string, customer, i.e. a dictionary that maps from strings to customer object, and that would be my customer lookup table. And I could have a dictionary that goes from string to list of orders, and that's my order lookup table. Or a dictionary of string, int, which is my word count if I'm writing a word counting program, etc., etc. And you see, the way you would use this is just like hash table, really, except you actually say what is the key type, what is the value type. You'll also note, if you've done C++ programming, that C++ has sort of this silly little anachronism where they require a blank between the greater than signs when you nest templates, and we don't require that in C#. So you can, yes, well, that takes applause, of course. You know, that is tremendously important. Type parameters can be applied not just to types, but also to methods. I've sort of tried to cook up a little example here of when that might be useful. Actually, the first method is probably not particularly useful, but it sort of shows the power of what you can do. I have a method called createArray that takes a type parameter t, and then I use that type parameter as the return type of createArray. And so I take a type t and a size, and then I return a new t array of that size. But perhaps a more sort of meaningful example is a sorting function that takes a t array. So I want to write an efficient sorting method that can take any array. But I can't, of course, add a sort method to array because I can't add methods to array. So instead, I can write a generic method and supply the type parameter in that fashion. And in use, this might look something like this, where first I call utils.createArray of string of 3, and back comes a string array with 3 elements. And you'll note no typecasts are necessary here, that the true type of the returned value is indeed string array. I then fill in my string array, and then I call utils.sortArray of names. And if you're paying attention, you'll note that I did not supply a type parameter in my call to utils.sortArray. Now, the reason for that is that C# supports what we call type inferencing. So we can actually, in most cases, infer what the type parameters are to generic methods. Indeed, whenever a type parameter is used in the parameter list of the method, we can make inferences about what the type is. And so in this particular example here, when I call utils.sortArray and give it a string array, if we match that up to t array, well, then we can conclude that t must be string. And since the user didn't say anything, we're just going to go ahead and pass string as the type parameter. So I alluded to constraints a little bit earlier. Let me sort of show by example here why constraints are important and what they do. Let's say I am writing the implementation of my dictionary class, and my dictionary takes 2 type parameters, the type of the keys and the type of the values. So in there, I'm likely to have an add method that takes a key and a value, each of type k and v. And In the implementation of add, I am likely at some point to want to compare my key to the other keys in the hash table. Now, one way I could do that is I could take the key parameter and cast it to iComparable or whatever interface, and then call the compare to method. And that's sort of what I traditionally would have done in sort of the old days. But if you think about it, what I'm doing there is, in a sense, I'm creating an implicit constraint on the type K. I'm saying K had better implement iComparable, or else at runtime this stuff is going to fail because the cast won't succeed. Now, generics are all about compile time stronger type checking, so what we provide is the ability to specify that constraint statically. So instead, I can say I'm creating a dictionary of K comma V where K must implement iComparable. Now, when I do that, two things happen. First of all, in my code, when I say key dot, all of the methods of the constraints of K are directly available without me first having to typecast. So you can see I can just call key dot compare to because we know that key will implement iComparable. And second, the compiler will now check every time I give a type argument for K. The compiler will check that that type implements iComparable, or else I get a compile time error. So you see how we've sort of put the constraint in as part of the contract of the class. Now, type parameters can have many different constraints. You can specify 0 or 1 base class, or any number of interfaces. And it's also possible to specify what we call a constructor constraint, which is new paren paren. And that means the type must have a public parameterless constructor, and when that constraint is present, it is possible to create new instances of that type in the generic class. Just sort of to show you the power of constraints you can write, I tried to make my constraints on my dictionary here arbitrarily complicated. So here's class dictionary of K comma V that implements iDictionary of K comma V. And then I say K must implement iComparable of K. So keys must be able to compare themselves to themselves. And then V must implement iKeyProvider of K. So from values I must be able to extract keys. And also iPersistable and new and so forth. And typically you would not write this many constraints, but it does show that you know you can actually be pretty expressive. It's interesting to sort of understand how generics relate to array types. If you've ever sort of delved a little deeper into the type system of C#, you will know that arrays in C# and in the CLR are covariant, meaning that, for example, if I have a string array, I am permitted to pass that as an object array because string inherits from object, and therefore object array, string array has a conversion to object array, and so forth. There are actually some costs associated with having covariance. Indeed, if I pass a string array as an object array, if you think about it, every time I put something into my object array, every time I store into an element, I actually have to dynamically check that the true runtime instance of that object array is string array, because otherwise, you know, I might be putting something of the wrong type in there. And indeed, every time something is stored into an array of a reference type, the jitter generates a dynamic type check. And there's some overhead associated with that. Without generics, you know, it makes a lot of sense to have array covariance. But covariance for generics is something that would be very expensive to implement. And we've actually made the decision not to be covariant, meaning that when I create, or in other words, generics are invariant. So if I have a class list of T, when I create instantiations of list of T, such as list of object or list of int or list of string, they are not related to each other inheritance-wise. They all, of course, inherit from object, but it's not as if list of string somehow has a conversion to list of object. Rather, they are two distinct types. Now, of course, sometimes it is nice to be able to do type-neutral operations. I might indeed want to be able to write some code that can operate on any list of T, or where T is not known. And what we recommend for that is the use of interfaces. So I could, in this example here, have my list of T implement iList. And if you look at iList, well, it basically has add and indexer and so forth, where all of the T's have been changed to object. and then in there are dynamic type checks performed and so forth that I write. And that way, I get sort of the best of both worlds. I get the performance of sort of not having to pay for covariance, yet I can still emulate covariance. A couple of other sort of interesting things about when you code with generics. Let's say I am writing a little generic method or generic class, but I have a type parameter in scope t, and I have a variable of type t. I am not permitted to say t, or say x equals null if x is of type t and t has no constraint. And if you think about it, it sort of makes sense, because t could be a value type. T could be any type here, and how could I put a null into a value type? So unless I've constrained t to be a reference type, I'm not permitted to set it to null. Now, of course, well, how do I get then the default value of t? How do I get a null or a 0 or whatever? Well, we support a new construct called t.default, which gives you the default value for any type. And for all reference types, that value is null. For all value types, it's 0. It's the value you would sort of get in a T array. You know, all of the empty elements are filled in with. Now, the interesting thing is that while I'm not permitted to assign null to something of a type parameter type, I am permitted to check whether it is null. And it's a nice little idiom here. Let's say I have foo of t again, where I'm passed some parameter of type t. And I want to see, well, when t is a reference type, I want to do something if it is null. If I write code like this here, if x equals null, throw some exception, what the jitter will do is, if t is a reference type, it'll keep the code and compile it in, and it'll exist. If t is a value type, the jitter will simply throw away that code branch, because it'll know t could never be null. Yet, so I now have a nice way of writing, you know, code that only executes for reference types and just sort of goes away with value types, which turns out to be very useful in many situations. Typecast, it's sort of interesting, again, that any conversion involving a type parameter always is either a boxing conversion or a reference conversion, and that means there are certain restrictions on what typecast you can perform, basically in order to ensure that you don't get yourself in trouble or get conversion. I'm not going to go into too much detail here. It's actually all covered in our documentation. What I will talk about, though, is all of the stuff that we're also doing in the base class library to support generics. Generics, as I said, it's not just a C# thing. It goes deep into the CLR and the other .NET languages. And with the Whidbey release of the CLR, we've extended the base class libraries with a new namespace called system.collections.generic. And in there, you'll find generic collection classes such as list and dictionary, sorted dictionary, stacks and queues, and so forth. There's also a whole family of generic interfaces that correspond to those classes. There's a set of collection-based classes that are convenient when you are writing your own collections. Let's say you're writing a customer collection or an order collection or whatever, and you want to sort of supply the logic that happens in when a customer's orders collection, when someone say customers.orders.add, you want to override that method and put some logic in there. That's what these guys are for, but they give you all of the base functionality automatically, so you don't have to do this forever repeating code expansion that previously was necessary. We also provide some utility classes, Nullable, Event Handler, and Comparer. I'll talk a little bit about Nullable afterwards. And finally, as I mentioned earlier, Reflection has been extended to fully support all of the capabilities of generics. Even down to reflection.emit, you can actually dynamically emit new reflection classes. Now, the Nullable type I personally like a lot because it solves a very real-world problem. Today, when people are writing database applications or dealing with XML schema or whatever, whenever you have a value type such as int or long or double, it's a pain that it can't be null. There's no good way to express nullable value types. So we've sort of dreamed up a variety of solutions, SQL int32 or what have you. Well, with generics, we can actually solve this problem once and for all by writing a type called nullable of t, meaning that you simply say nullable of int or nullable of double or nullable of long or whatever, and that way you get a generic way of expressing nullability. A nullable of T is basically a little struct that combines a T and a bool, and the bool says whether the T is defined or not. There are conversions between T and nullable of T. Indeed, there's an implicit conversion from T to nullable of T, and there's an explicit conversion in the other direction. There's a conversion from the null literal to nullable of T. And sort of to sum it up, it means that I can write code like the stuff here, nullable of int x equals 123, or nullable of int y equals null. And then later I can check whether x has value, and if so, get the value, etc., etc. So that was generics. I'm going to now move on to anonymous methods. And I'm just going to sort of lead out with an example here because I think it's a good way to understand the feature. You've all seen code like this. You may have not written it, but you've certainly seen it generated by the Windows Forms Designer, ASP, or something like it, where you're setting up a form and you have a button, and then the button has an event handler, and you want to attach some code to it. And today, there's sort of a fair amount of plumbing that needs to happen here. You know, you have to create a new delegate, plus equal it onto the event, and then you have to put the code sort of with a level of indirection in a method that the delegate points at, and you have to write the whole argument list, and et cetera, et cetera. With anonymous methods, you get to write the code right there where you would like to say it. So you get to simply say add button.click equals, and then you just write the little snippet of code right there. Thank you. So in a nutshell, anonymous methods allow code blocks to be written where delegates are expected. And then we will automatically infer the delegate type. Indeed, what we do is we take this little code block that you write, and we hoist it into a method, and then we create a delegate to that method, and then we cache the delegate, and we sort of optimize the heck out of it and create as few of them as possible, and so forth. So we're sort of doing the work that you would have otherwise had to do manually. Now, anonymous methods come in two forms. If you don't care about the arguments that the delegate is providing to you, you can just say delegate, open curly, write some code. If you do care about the arguments, you can say delegate of argument list, open curly, and write some code that uses the arguments. And as you can see here, especially the bottom one, really sort of looks like an anonymous method, a method named delegate, if you will. So that's all good and well. Now, where it gets really interesting with anonymous methods is when we sort of get into the space of closures and lambda functions and whatever. I don't know if anyone of you have ever done Lisp programming, but anonymous methods really are lambda functions, if you know Lisp. And they do indeed support the same things that lambda functions do, and that is the ability to capture outer variables or local variables. Now, I'm going to show you by example why that is interesting. In our class library, the list of T class that we provide has a method called findAll on it. It's a darn useful little method. I'm sure you've all done this at one point or another. You have a list, and you'd like to find all of the elements in the list that meet a certain condition, and then you'd like to get a new list that contains those. And the way you could write that is you could write it as a findAll method that takes a predicate, which is a delegate function taking a T, returning a bool. And then in the implementation, you new up the result. You sit in a for loop, you for each of all of the items, and you call the filter method. And if it says true, then you add them to the result, and then you return the result. In use, it might look then something like this. Let's say I'm writing a bank class, and in my bank I have a list of accounts, and then I want to have some convenience methods like get me the overdrawn accounts, for example, and returns a list of accounts. And the way that's implemented now, I'm using this nice findAll method, so I simply return in overdrawn accounts, I return findAll of a delegate that checks whether the balance is less than 0. And you see that I get to sort of write the little expression right there and pass it as an argument. And this is, in a sense, a higher order function, as it's known in functional programming also. Now, I might also want to have a method that returns me all of the large accounts, but being a large account is actually something that's decided by a parameter. I don't have a fixed amount that says it's large. You get to specify a minimum balance, and then I get back a list of all the accounts that have a balance larger than that. And here you see, again, it's done the same way, accounts.findAll of a delegate that takes an account, and then check whether balance is greater than equal to minimum balance. Now, if you look at this code for long enough, you might sort of start to realize that there's something fishy here. That like this thing takes a parameter minimum balance that I'm then checking in the delegate. The delegate gets passed to the findAll method. What if he takes that delegate and stores it in a global variable and then calls it later? Where does the minimum balance local variable come from now? You know, how can I refer to it when the method has already returned? Well, what we do is when you capture an outer local variable, as it's known here in techno speak, when you refer to an outer local variable or parameter, we do a code transformation where we create a helper object and put that local variable as a field of the helper object and put the helper object in the heap, such that we can extend the lifetime of the local variable. Indeed, the transformation that happens to get larger counts is that we inject the code in yellow here. So we inject the helper class, and we move the min balance into a field of the helper class. We move the code that you wrote into a method of the helper class, and then we create a delegate to that method in the helper class. Now, you may go, gosh, well, geez, this is objects created behind my back and whatever. I don't feel good about that. And true enough, but you know, the thing is, if you had to write this code yourself, this would be your only alternative. Or you might, even worse, actually start doing stuff like, you know, oh, I'll just put it in a field here. Now it's really not thread safe anymore, but you know, it's not multi-threaded, so it'll probably work and so forth. And it turns out that that this kind of stuff is actually, it enables a whole new kind of programming. It's almost like it allows you to create new statements, because code can now be passed as parameters, and you can have your own statement that takes codes as parameters. And you know, this is what functional programming is all about. And making it into language constructs gives us the ability later on to do even more aggressive optimizations of it. So I'm pretty excited about this stuff. Now, as a side effect, actually, of anonymous methods, we also get one thing that I call, again, terrible name, but we call them method group conversions. What it boils down to, though, is that we can pretty much infer delegate types everywhere, and going forward, you will very rarely have to write the name of a delegate type. For example, here's sort of a classical example. The thread object that we have in the class library requires you to pass a delegate to the code that gets run when the thread is started. So you always end up having to write new thread start of blah. And with anonymous methods, you simply get to say new thread of blah, and we infer what the delegate type is. We automatically create it, cache it, etc., etc. Thank you. Okay, so that's a little bit about delegates and anonymous methods, and I'll try and do a little demo here where I show both of those in action. I've written this little test harness here that allows me to test the performance of stuff, you know, sort of in the large. And so I have a class test that represents a test case. And for each test, I have a name and the code that I want executed when the test runs. And I've expressed the code as a delegate of, you know, type void, taking no parameters. So it's just a piece of code I can call and wait for it to run and then time how long it took. Then in my program, I have a run tests method that takes a params array of tests, so any number of tests that I care to pass to it. And what it does first is it runs each test once to sort of prime the pump and get everything jitted and good and ready to go. And then it falls into a loop where it runs each test 1,000 times, capturing, you know, the time that it took. And then it calls a draw bar method here to draw a little bar that shows the resulting time. And draw bar then, well, I started writing this as a Windows Forms app, and then I realized, gosh, we have all these neat extensions to the console class. We've actually reintroduced the ability to control the colors of the console class, just like you could in the old DOS days. You know, it's deja vu all over again. So I cheated, and I draw my bar simply with character graphics. This is something I'm good at because I'm such an old fart, you know. So here it is, and basically, you know, it just draws the bars. And then here's my main application, run tests, and I pass in a couple of tests in this case, but you know, I could just keep sort of passing more. And you'll note here that each test I new up, I give it the name of the test, and then I write a nice little anonymous method, and then I write the test right there in line. I'm passing code as a parameter, if you will. Now, the tests themselves here start out simply by timing array lists. I time out how much time does it take to create an array list, put an element into it, and remove it again, and the same with array list of ints. So let's try and run that and see what the results are. So array list of string takes this long. Array list of int, interestingly, takes a little longer. The reason being that every time we put an int in there, we have to box the int, allocate it in the heap, et cetera, and so there's cost associated with that. Now let's try and modify these tests here to use generics instead. So we'll just simply copy these tests here and then paste, and then let's go back up here. And then let's first take our string test and change it into a list. We'll call it list of string, this test here. And then, we will erase this line here. And then we'll say list of string. And you'll note, again, statement completion, everything works with generics. List equals new. And here, the system automatically pre-selects new list of strings, so I just type paren. I don't have to actually type all of that stuff. And then I can now get rid of the typecast because my list is a list of strings, so I don't need to cast the result back to string. And let me do the same transformation on my list of int. So list of int test, and here, let's select this guy, delete it, and then I say list of int, list equals new list of int, and again, let's get rid of the typecast down here. So now we have 4 tests instead. So let's run and see what happens. And we get the first, same 2. But now we see, first, list of string runs a little bit faster than array list of string. Primary reason here being that we don't have to downcast the result, so we sort of save ourselves one typecast. But list of int actually runs more than twice as fast as array list of int because we are truly running code that manipulates ints here. It's not, boxing or any of that stuff. So as you can see, generics, give you not just stronger typing and benefits, but there's actually also performance associated with them. Thank you. Next thing I wanted to talk about is iterators. I'm sure you've all used the for each statement, and for each relies on what we call the enumerator pattern. Basically, the thing you're for eaching on must have a get enumerator method that returns a thing of a particular shape, and when you write for each object in some list, we turn it into some code that obtains an enumerator and calls get, move next, etc., etc. For each definitely makes it easy to enumerate collections, but if you've ever had to write an enumerator, you will have realized that it's hard. How many in here have actually had to write an enumerator? So I'm surprised at how many people. That's great. You'll like this stuff then. Let's just go back to our list example again and say, what does it take to write, a list that has an enumerator? Well, first I have to write a method called getEnumerator that returns some new object that I then have to go implement. In this case, I called it listEnumerator. And that thing minimally looks like this. A class that implements IEnumerator. It stores a back pointer to the list, an index of how far it's gotten, and then sort of sets itself up, and then a bunch of state machinery in the move next method that checks the boundary condition, et cetera, et cetera. Now, keep that in mind, and then let me first talk about iterators conceptually, and then I'll show you how it all sort of comes together very nicely. Methods, if you think of regular methods, a regular method is a thing that you can call. The thing then does a bunch of work, and then it can optionally return one value at the end. And the way you invoke a method is you write a method call. An iterator is a thing that can incrementally compute multiple values, and it can amortize the work over time. The way you invoke an iterator is through a for each statement. So when you for each on something, the iterator gets invoked, it gets to do a little bit of work, and then it can yield a value. it yields a value to the for each loop, which then consumes the value. And when the for each loop goes around, then the control comes back in the iterator right after that yield statement, and you now get to do more work to produce the next value. So they're sort of like production and consumption, and you can now sort of write code that produces multiple return values over time, and they are consumed by for each statements. Now, the way we enable this is through two new statements, yield return and yield break. There's been some debate already about why did you pick these funny words, yield return and yield break. Well, it has to do with ensuring that we break no existing code. If we'd introduced a yield statement, then yield couldn't be an identifier anymore, and then all sorts of financial apps would have broken. So we didn't go that way. Now, the thing that's cool about iterators is that when you write an iterator like this, an iterator is basically something that returns an enumerator or enumerable, and it can yield multiple values, and then you consume it with a for each. But when you write it that way, we transform your code that you write in the iterator into an implementation of the enumerator pattern. So from the CLR perspective and other languages' perspectives, there are no changes, and they can just, with their for each statements, consume iterators that you write. Indeed, the transformation that occurs is really that we take the code that you put in the iterator and we turn it into an enumerator class. We hoist the code into the move next and put a state machine around it, etc., etc. The thing that's cool about this is that you now get to write sort of very, very usable convenience methods. Like, for example, our list of T might have a get enumerator, and it would be written something like this, where, you know, I for each, and then I yield each element. But I could also, sometimes I want to be able to for each in descending order, or I want to for each on a subrange, and by writing iterators, I can do that, and now I get to write nice code like this, where I say for each x in items, or for each x in items dot descending, or for each x in items dot subrange of x comma y. And thank you. So that's basically what iterators do. Now, partial types essentially solve two problems, interestingly, that sort of happen to coincide. First of all, we have, on numerous occasions, we've had people ask us for supporting include files. And we go, well, why do you need include files? We go, well, because my class has gotten enormously large and I need to split it up. And, you know, well, we go, well, maybe your class shouldn't be so large. But that usually doesn't resonate. So and honestly, there are good reasons sometimes why classes get large and why you want to split them into multiple pieces, you know, that multiple developers can work on without serializing each other. So that's one problem. Another problem that we've observed more and more is that increasingly, we rely on automatically generated code in our development tools. This isn't just us, it's everybody in the industry. You know, we have object mappings, we have automatic UI generators, we have things like, you know, web backends like ASP and so forth, and key to them all is that they generate code. But if you've ever worked with something like an OR mapping or a UML tool, you'll note that, you know, typically the code that it generates isn't quite right. It's really more like a skeleton, and then you have to go in and modify the code. But once you modify the code, if you ever have to regen it, then you step on your own changes, and now you're sort of caught in a bind there. You know, you're damned if you do, and you're damned if you don't. It turns out that partial classes can solve that problem as well, and I'll show you how. So, in a nutshell, partial classes allow you to split the declaration of a class or a struct into, or an interface, into multiple disjoint pieces of source code that can be in different source files. And then at compile time, the compiler puts the pieces together. Let's say, for example, I have a customer class written as a partial class, and I have sort of one part that declares all the fields and another that contains my higher order business logic. When I compile those two source files together, the compiler merges the two fragments into one class and then compiles that, and that becomes my resulting output. Now, you can sort of see here what it is I'm talking about. Of course, this solves the include file problem because you can split your class into multiple pieces now and put them in different source files. But you can also see how some of those source files might be auto-generated, but others are the ones that the user writes. And now, when you regen the code, well, you're only regenning one of them, so you never step on the source code in the other file. And this actually turns out to be a very useful paradigm for working with auto-generated code. Indeed, it sort of is the underlying mechanism behind the code beside feature in ASP.NET and in Windows Forms that we'll support in Whidbey. And with that said, let me actually try and demo that. Let me close this, this project that I have here. And then let me open another project. Here I have a very simple little Windows Forms app. Nothing magical there. But I've actually used a partial class behind my code. So if I look at my source code first for form1.cs, you'll note that all that's in there is just a constructor. And you'll also note that there's a partial keyword on the declaration of this guy. Now, if I go back to my Solution Explorer, I've actually expanded it here to show all files. You'll see that Form1 has a dependent file called form1.designer.cs, which is the file that the designer spits into. And we could go look at that code. And here you see all of the designer-generated code, which sits over in this other partial class fragment. And when my app is compiled, the two are combined. And so, the illusion is that there's just one. Well, there's not an illusion. There is only one class. Now, let me show you how deep this is integrated in the IDE. If I go back to, if I go to my designer here, and let's say I grab myself a button, put that on my form, and let me grab a text box, put that on the form. And let me go back to my, let me actually just double-click on button 1. And you'll see it inserts an event handler here, but nothing else has changed in this particular file. Yet, when I do statement completion and I type text box 1 dot, you'll see that there's a text box 1 in scope, and indeed there's a button 1 in scope. Those are actually declared over in the other class fragment, but IntelliSense has put the two fragments together, so the IDE knows about partial classes, and so you essentially just sort of have the illusion of a very simplified world here where you have an instance variable for every UI element, yet if you care, you can drill down and see what's really going on. So that's partial classes. Next thing I was going to talk about is all of the other enhancements that we have in the Whidbey release. First, static classes. And I sort of have, let me first explain what they are. Static classes are basically the ability to say that this class contains only static members and have the compiler check all of the restrictions that logically follow from that. There's a little anecdote that goes with that motivates this feature. Late in the RTM cycle of the first version of the .NET framework, we realized that in certain shutdown scenarios and in certain destructors of some objects, we sometimes needed to check whether the system was in the process of shutting down, and if so, then let's not release this handle, otherwise let's, and so forth. And so someone went and added a method called, or a property called, no, actually there's a method called has shutdown started to the system.environment class. They added it as an instance method, but it turns out that system.environment contains only static methods, and it has a private constructor, so you could never create an instance of it. And therefore, you can never you can never call that instance method that they added. So I guess we proved to ourselves that, our QA guys were sleeping. and secondly, that no one actually needed this method because you couldn't call it. Now, it turns out, though, that if you look in the framework, and I'm sure in your own coding, it's a fairly common pattern to create these classes where you have only static members, and then you sort of follow the pattern of having a private constructor, and you make sure to not ever create instances and so forth. And we're just essentially formalizing that in the language. So you can now write something like public static class math. And what that does then is, first of all, ensures that you can only have static members. If you try to write an instance member, we give an error. Second, we say it's an error to have variables or parameters of this type because it's meaningless. You could never have instances. And system.console, system.environment are good examples of classes that use this pattern. So that's static classes. Property access or accessibility is, interestingly, it's a very little feature, but it's one of the most commonly requested features. It's the, well, I haven't even said what it is. It is the ability to have different accessibility for the set and get accessor of a property. In particular, it's typically that you have a more restricted setter than a getter. For example, a public get with a private setter. Here's an example in my slide where I have a customer ID property that anyone can look at, but only people in the same assembly are permitted to set the customer ID. Now, the way it works is that we permit, when a property is a read-write property, that is, when it has two accessors, we permit an additional accessibility modifier on one of the accessors, and that modifier must be a strict subset of the property's own accessibility. So you can, in a sense, restrict one of the accessors more than the property itself. That's basically how the feature works. Namespace alias qualifier. It's sort of down in the deep stuff here a little bit, but one of the things that we sort of have observed over time is that when people write code generation tools, sometimes you run into versioning issues where, you know, the code generator wants to make sure to generate a reference to, say, system.console.writeLine. So it literally gens system.console.writeLine to be absolutely sure that it gets that one. Well, unfortunately, if the user introduces a member named system in his class or something, well, things start breaking because there's no way of ensuring that the lookup starts at the global namespace. And basically, that's one thing that we're addressing with the alias qualifier. The ability to say global : : and then here's where the lookup starts, and you always know what you're going to get. The other thing that we are enabling is use of this : operator with using aliases. So in my example here, I have using IO equals system.io, and then you see me referring to IO : stream, etc., etc. Now, the way the : operator works is that on the left-hand side of the : there must be a namespace alias. And we look up that identifier only as a namespace alias. So the only way we look it up is we see if there's a using declaration for an alias called IO. Now, what that guarantees is that it is impossible for things to break because of versioning, because there's no way that someone could introduce a namespace alias in your source file. So if you write your code this way, where you create aliases for all the namespaces that you're referring to, and then you use this form of lookup to get at the members of the namespace, you can guarantee that your code will not break because of versioning issues, that it will not break when new identifiers or new types or new namespaces are introduced. And that's important. We actually have some groups inside Microsoft that like to do that additional work up front and then get the benefits down the line. Fixed size buffers. Now we're really down into the deep grovelly stuff here. It's really just sort of fixing a thing that we were missing in the initial release of C#, which is the ability to create inline arrays in unsafe code. And we have here, you see sort of the syntax where, for example, in Windows, let's say you're writing some code, you're interoperating with the OpenFile struct in the Win32 API. Well, the OpenFile struct has an inline character array for storing the path name, and this gives you the ability to actually faithfully declare that struct for interoperability, where previously we did not allow you to have these embedded arrays. Finally, pragma warning gives you the ability to control individual warnings in your source code. So here is what I actually consider a fairly real-world example where you want to turn off an obsolete warning in a block of code. And you can do that with pragma warning disable. And you'll note that it's not pragma warning disable and pragma warning enable. It's actually pragma warning disable and then restore to previous state. So you don't have to know whether it was on or off before the code. So that is sort of a big roundup of all of the new features in C# 2.0. I wanted to just mention a little bit C# and standardization. I don't know how many of you are aware, but C# is actually a standardized language. It's standardized by ECMA as well as ISO. The ISO ratification happened in April of this year. And I just want to basically reiterate to all of you that we remain very committed to standardization of C#. All of the features that I've shown here today were submitted to ECMA actually more than a year ago at this point, or close to a year ago. Some of them have already been adopted into the upcoming ECMA 2.0 standard. And we are committed to this process, and we continue to work with ECMA and submit all of our stuff. Thank you. Finally, now it's time for the commercials. We finally got our stuff together and actually put the C# programming language specification into a book. It's called the C# programming language. It was actually just released this week. And Scott Wiltermuth and myself are doing a book signing tomorrow at the Exhibition Hall bookstore from 1 to 2 o'clock if you're interested in getting an autographed copy. And with that, I just want to give you some pointers here on, first of all, to the C# language homepage on MSDN. We have, last week, we put up all of the specifications for C# 2.0, so I urge you to go there. It's a complete technical specification of all of the features I've talked about today. The C# standard, here's where you can find that. There's a panel on the future of .NET languages that I'm on Thursday that you might want to be interested in attending also. And then finally, we have a tools lounge right after this talk, and also on Wednesday in the area that's right out here on that side out here. And with that, I'll open it up for questions here. I think there are some microphones. Yep, I think people are already lining up. So thank you for coming. Let's start over here.
I have two questions about generics.
Okay.
If you could go back to the slides, question was specifically about one of the bits of code you did that looked strange, and I wanted to ask you how it actually works.
Okay, I don't know if I am going to kill the, well, I'm just going to go back here. Let's see. Which one? Was it that one?
Keep going.
Okay. That's fine.
Next.
Here it comes. Here?
You can see your hand.
I think, yeah, the next one.
Next one, okay.
I think
this
it was.
One. No?
Maybe it was the next one.
Now we've gone through all of them. What was it specifically about? Maybe you can just sort of explain it and I'll know what slide it is.
There was a situation where you didn't seem to have a constraint and something seemed to need a constraint.
Uh-huh.
Which is also kind of part of my second question.
Yeah.
Which is sometimes you might want to use the same generic on two unrelated classes that you got from someplace else that have a lot in common but don't technically implement the same interface.
Uh-huh.
And it would be very nice to be able to say, we can infer an interface, that I can declare an interface and say any class that could possibly have this interface, I can cast that interface or treat that way.
I think I know what you're asking here. Let me try and find the particular slide that we're talking about. Actually, it's the other way. So here we go. When you write constraints on a generic class, we give you a certain set of things that you can say. You can say one base class, any number of interfaces, and you can say the constructor constraint. We had a lot of discussion in the language design group about sort of what is the ultimate constraint system that one could imagine. And the sort of design we arrived at, or speculation that we arrived at, was the notion of named patterns. Imagine that you can name a pattern of number pattern number, open curly, has an operator plus, an add, and a blah, and an operator equals, and then any type that sort of adhered to that pattern would automatically satisfy that constraint. It turns out that is tremendously complicated to implement using, the code sharing strategies and whatever that we have in place currently, and we think that rather than sort of try to invent the ultimate Rolls-Royce of constraint systems without really knowing whether there's a need for it, we're sort of proceeding with caution here. I think we've identified sort of the 90% scenario with the constraint system that we have in place now, and we've left the door open for future enhancements. And there are some interesting patterns already that I'm seeing from users that are using generics that I hadn't even thought about. So some of this stuff can actually be done in other ways, and we'll be writing some articles about that and so forth.
Are we going to use multiple inheritance in the future?
Where's the person asking the question? I'm sorry, I can't.
Yeah. He's in the middle?
He's in the middle. Okay, great.
Yes.
What middle? The other middle.
Yes.
Okay, go ahead.
Are we going to support multiple inheritance in future? Multiple inheritance?
I can't.
He's asking about multiple inheritance.
Yeah? Oh, multiple inheritance. No, would be my sort of short answer. We are not thinking about multiple inheritance. What we are thinking about is a thing called mix-ins that you can do with generics, actually. It is not possible to do it with our current generic system, or at least it's not easily possible, because we do not permit you to inherit from a type parameter. But if we lifted that restriction, you would be able to write mix-ins and get a lot of the benefits of multiple inheritance without the pain. And I think that is probably the path that we would consider going forward. Let's take one over here.
Yeah, I had a question on partial. Currently, I think you don't support mixed languages. Is there any possibility in the future where one function could be written in C++ where you're doing interoperability or something that's easier, or Windows?
It is correct that currently partial classes are purely a compile time thing, and I think they will stay that way. Which means, yes, you cannot write one fragment in VB and another in C#, because at compile time we put them together, and there's really only one class. We don't currently have any plans to change that.
What does the class have to do with how the code was written? I mean, when you're compiling it into CLR, what do you care?
Well, in theory, you could imagine some sort of hybrid compiler where we could compile both VB and C# code in the same compiler, and then it would be possible. But it's not a direction that we're actively pursuing. I have yet to get a lot of requests for it. Anyone over there? Nope. Let's take the next one over here.
I had one follow-up question. Another question, and that was thread safety and iterators.
Yes.
Or self-modification. How do those?
Okay. Thread safe. That's a good question. Iterators are thread safe. That is, the code that we generate for iterators is thread safe in the sense that we will never hand out an iterator or an enumerator object to more than the same enumerator object to more than one thread in the code that we generate. Now, the iterators themselves are not meant to be shared across threads. I mean, that's kind of a meaningless thing to do. But the instantiation, i.e. the implementation of the getEnumerator method that the compiler creates, is thread safe.
But what about if the object is deleting its own items after the iterator was created? Is there an error thrown, or?
No, that is. We don't solve that problem. It is up to the object to coordinate that by itself. I don't know if there are people. Is there one over here?
Yeah, my question is about generics. Suppose if I want to create a list of employees who can take, which can take manager as well as a normal employee. Manager is a derived class of an employee. Do you support that scenario?
I'm not quite sure I understand what the scenario is.
Suppose if I create a generics which is a list of employees.
Yes.
Can it take the derived class of employee also, or only you allow employee types?
Sure. No, you can. An iterator. If an iterator says it returns employees, then it can also, of course, return anything that derives from employee. Yes.
My question is generics. Suppose I have a list of employees. Can I add a derived class of employee instance into the list?
Yes, you can.
Thanks.
Far right.
Far right.
Oh, over here.
Okay.
If you have an existing interface
Yes.
that's in part of the .NET framework, like iDataReader, it's basically developed over the object. Is there a way to use a generic to basically specialize that?
No, but we are definitely considering having generic versions of DataReader. Indeed, I don't know if you've gone to any of the talks on object spaces and whatever, but object spaces will indeed use generics and provide you with a record or a data reader or object reader of customer, for example, that allows you to actually have a strongly typed data reader. So it is something that we are doing. Let's take one here.
Okay. Since it may take a while before the next version of .NET and the runtime gets widely adopted by enterprises, and since a number of these enhancements have been through injecting classes behind the scenes and are compile time based, like the anonymous methods and partial classes, would it be possible then to, using the Whidbey C# compiler, to compile with some of these features that don't require like changes to the jitter, the runtime, into 1.0 and 1.1?
I believe that's possible. Don't lynch me if I'm wrong, but you obviously would not be able to use generics because generics require support in the runtime. But anonymous methods and iterators, partial classes, that should work. But technically it ought to work at least. Yeah.
Hey, my question is about yield. And can I yield the reference objects? Meaning an object is created in the method. Can I yield it and store it in the enumerator?
Yes, I mean you can yield. Yes. Absolutely.
Okay, and the other question is, in the method there are certain data which I yield already. I want to get rid of it and send some other thing. Is it possible?
Well, once you've yielded it, it's sort of gone. I mean, you don't. Nothing is holding on to it after you yield it because it just goes through the enumerator and the for each consumes it, and that's that.
Okay.
Yeah.
Thank you.
Okay, let's go over here.
Hello, Anders. I just wanted to ask, is it possible to constrain the type passed in to a generic class to be, say, primitive? Or if you wanted to reduce the scope to, say, a numeric type, is that at all possible?
No, not directly. You can constrain to a base class, but you can't constrain to primitive or array or some of these other things that don't sort of have a root type in the type system. Indeed, you might think that you could constrain to system.valueType, which is the root of all value types, but we don't permit that because it's actually not really what you would want, because system.valueType itself is not a value type. So you would sort of constrain it to all value type and one reference type, which is not really the right thing either. We're looking for whether it is really necessary or not, because I mean there are very few things that we would do if we permitted you to constrain to value types. I mean, about the only thing is if we knew that T is a reference type, then we could permit you to assign null to values of type T, but that's about the only thing that it would enable. There is a pattern that we recommend for more complicated constraints, which is that you write a static constructor in the generic class, and in that static constructor you can apply reflection to T. So imagine that you have a list of T and you want to require some bizarre thing on T. Well, in the class constructor of list of T, you can say you can obtain type of T and then do the appropriate reflection on T to figure out whether it meets whatever constraint it is that you require it to have. And if not, then you can throw an exception. It's not ideal. I mean, it doesn't give you compile time type checker, but it actually throws an exception before the code ever runs at runtime, and it only throws it if you ever try to create that type instantiation. So at least it turns out to be fairly useful to do that.
Thank you.
Okay. Let's go over here again.
Will it be possible to specify a default constructor for value types? Because I found it a bit problem, because value types are very, very good for type writing, but you can give a default constructor.
Correct. There's no work currently to permit that. I can sort of talk a little bit about why it is the way it is. So every value type has what we call a default parameterless constructor that zeroes out the instance. The existence of this constructor is actually an illusion. It doesn't even exist, but we provide you syntax for it. And the reason we have it is that in order to guarantee type safety in the system, we pre-initialize, in a lot of cases, we pre-initialized instance data. For example, we pre-initialize arrays to some value, or we pre-initialize instance variables in classes and so forth. And the value that we put in there is this default value. And you know, as much as we throw ourselves about, you know, there's really no way to get rid of that value. That value will always possibly exist in an array or whatever. And you could say, well, when you knew an array, we ought to call the parameterless constructor on every element in the array. And you know, now we're adding a bunch of overhead. And what if one of them throws an exception? Do we keep going and initialize the other ones? And if we don't, well, then you do indeed observe that value. And so rather than like try to like sort of like maybe sometimes do it, we just sort of said, nope. This value, every value type must be prepared to deal with. And it just sort of gets it out of the terrible mess that's called copy constructors and assignment blah, blah, blah operators that you find in C++, where you're never really quite sure what happened here and then whether it happened and so forth. So that's sort of my long answer.
Yes, but building a system, a list of types, for example, my custom types begins very difficult because there are too few operators overloadable in C#, and I don't find it very good.
I have heard people say that, and then when I drill a little bit, it turns out that we had a philosophy when we designed operator overloading in C# that basically said we want to support the ability to create operators that truly are operators. That is, operator plus takes two values and returns a new value that is completely unrelated to the other two. So a strict functional side effect free view of operators. That view we completely ascribe to, and that view we want to support fully. There are many other views of operators. C++ sort of...
No, but stay on the types. I mean, I don't want to treat all my objects like a type. Stay on the types. For you, in the default classes, in the default set of classes, I miss many real types. The fraction type isn't implemented. If I want to implement it, I need a value type because...
but you can write that. Maybe we should take it offline. Actually, I'll be at Ask the Experts and the lounge, and let's talk about it and then see if I can address your problem.
Okay, thank you.
Okay, let's go over here.
My question is, it would be nice to use iterators, for example, to traverse a recursive data structure like a binary tree. Can you do that?
Yes, you can do that. The way you do it is that within the iterator, you for each on the left, and then you for each on the right, and then you yield yourself, or you know, whether you want to do in order or pre-order or post-order. It is possible to do it. It does end up creating sort of recursive calls, as you call the current property. You sort of recurse all the way in and out again, which is not ideal. But the only we are thinking about alternate ways of code-genning that. I mean, you could argue that we should consider coroutines and whatever, but that's a whole different ballgame and a much, much bigger undertaking and would require support in the CLR. And I'm actually not adverse to supporting coroutines, but I think it's an orthogonal issue. And what we just wanted to do was to make it easier to write simple iterators
Does that mean that it's allowed to use the yield command outside the iterator method?
No, you're not allowed to do that. So you can only yield in the iterator itself. Yeah.
How about stock implementations for interfaces? Like
yes, it's something that we continue to think about, and we may do it. I think the way we would, yeah, well, it sort of depends. Are you talking about like having the ability to just say, I want to implement this interface and here is the implementation, or are you talking about the ability to just sort of have default methods on interfaces?
What I want is to be able to have an interface on 20 different classes and to say these 10 classes should use that implementation and those 5 should use another kind of implementation.
Yes. So you're talking about default interface implementation through delegation, basically.
Yeah.
Yes, yes. And it's something we continue to think about. I must say I don't often get the request for it, but you know, it's right there.
I think it's very powerful.
Yeah. And I've seen solutions where you sort of say delegate through this instance variable or this property or whatever.
It's possible to do it manually, but it would be nice if the language could do it for me.
Yeah. No, it's a good suggestion. I've heard it before, so I'll think about it.
Thank you.
Let's do the next one over here.
The current crop of built-in collection classes does not always XML serialize well or at all, whereas native arrays XML serialize quite nicely as long as it's an array of something XML serializable.
Okay.
What about the crop of upcoming generic collections? How will they support XML serialization?
So the whole serialization infrastructure, actually I think there are talks on that in the Indigo tracks that you should go, because I can't give you a simple answer here. We will support serialization of all of the generic classes in the existing serializer, and I believe also in the XML serializer. But there's much more stuff than that you would find interesting. I'll take a last question, and then actually well, you know what? I won't take any more questions because they're booting me off the stage. But come find me out in the track lounge out there or at the Ask the Experts later tonight. Thanks for coming.